Now I'll show you an even more surprising comparison of two infinite sets. It's this comparison. This will be a proof that there are more real numbers than natural numbers. Now you might have suspected from the previous proof that I showed, where I showed that rational numbers and natural numbers have the same size, or cardinality, that all infinite sets are going to have that property. Well, it's not true. There are infinite sets that are, in a sense, strictly more infinite or larger than other infinite sets. And the simplest one for me to show is that real numbers have more numbers in some sort of absolute sense than the natural numbers. So this is a bit surprising. I hope you enjoyed this one. All right. First thing I want to recommend is that if you haven't done it already, listen to the previous segment. The previous segment proof. Okay, because the ideas we use there will be repeated here. And again, this proof that I'm going to do is due to the same man as before. This man's name is Cantor. He did this in 1874. Okay, the first one to be able to think about infinity in this way. And this proof is even more exciting. This proof is even more surprising, let's say. Okay, this was something that at the time certainly, and even now if you haven't seen this, may surprise you. Okay, here's what I'm actually going to do. I won't attack the real numbers as a whole. I'll take a small subset of them. Watch this. There are more real numbers in the open interval from 0 to 1. That's all I need to check. In the open interval 0 to 1, then there are natural numbers in all of n. So I don't even need to compare all of the real numbers with n. I am just going to compare the numbers between 0 and 1, not including 0 or 1. Now that's really even more surprising, that a small interval like this alone has more numbers than the natural numbers. All right, here's the proof. And again, this will be a proof by way of contradiction. This will be the same kind of thing we did with the square root of 2 earlier. First, this is how the argument will go. First, we have to be able to talk about the real numbers that live in this interval from 0 to 1. So we'll talk about their decimal representation. So recall that all real numbers in that open interval 0, 1, which is this interval, by the way. Let me go ahead and draw the picture here. There's 0, there's 1. Talking about the interval that does not include 0 or 1, but does include everything that's in between. So this interval corresponds to that on the real number line. All the real numbers in that interval can be written as decimals, which we've seen before, as decimals of the following form, and I'll put that on the next page. And this will be crucial to our proof because we want to be able to refer to all of these numbers so that we can match them, or at least try to match them, with all the natural numbers. And here's the form they take on. Point A1, A2, A3, dot, dot, dot. The A1, A2, and A3 will stand for digits, as I will mention in a moment. Or they might look like B1, B2, B3. I'm just using different letters to indicate that these are different numbers, C1, C2, C3, and this will be out to infinity, so that will go on forever. So this is how all of the numbers in 0, 1 look. They have nothing to the left of the decimal because they are fractions, after all, between 0 and 1, where, just for the record, the A's, B's, and C's are all digits. Okay, they are all digits from the set of digits, which is, of course, the set 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so those are all of the numbers in 0, 1 can be represented as these kinds of forms. Okay, I am going to claim, and this is something I'm going to hope to contradict, I'm going to make the following claim. In fact, I'll put here, which we hope to contradict. Which we hope to contradict. Okay, this is this. I'm going to set this up and then knock it down. Here's the claim. The claim is there exists somewhere, somehow, a one-to-one correspondence, which again, if you like, you may call a matching, as long as you know what it means, a matching between these decimals that we just saw, these decimals in the open interval 0, 1 and n, all of n. Okay, that is my claim, and I'm hoping to be able to contradict that, because then I will have my proof. Well, okay, suppose we have such a one-to-one correspondence. We have such a matching, say, so that I can write it a little bit more simply. Suppose we have such a matching, as shown. Okay, I'll show that on another page here. And the matching, there's nothing particular about this matching. This is simply a 1, 2, 1 matching, as we've done before. And over here, I will have the natural numbers that I'm matching up. So this side over here will represent the natural numbers. And then over here, I will have all the decimals, which, if there is a matching, have to be listable like this: B1, B2, B3, C1, C2, C3, etc., going out to infinity. This represents the open interval 0, 1. And of course, here is the matching, or an example of such a matching, like so, and that will continue out to infinity. So if there is such a one-to-one correspondence, the natural numbers are listed here. All the decimals have to correspond back to them. So they have to be listable, if you will, just like that. Well, if this is a correspondence, a typical correspondence, I'm going to show that no matter what correspondence you have, there's got to be something over here that's missed. Some number in 0, 1 that this correspondence will miss. So what I will do is we'll now construct a decimal in that open interval 0, 1, which is missed by this correspondence, which is missed by this correspondence, or any correspondence. There's nothing special about this one. The only thing that's mentioned here is what is common to all the correspondences, that the right-hand side must be listable to compare to 1, 2, and 3. Okay, let me show you what the construction is. Let me build the decimal I said I would build. So we'll construct the following. We'll construct the number x, which will be the decimal point x1, x2, x3 out to infinity. So this is the decimal I'm about to construct. Now let me tell you how I'm going to choose the x1, x2, x3, where x1 is any digit at all, but it is not equal to a1, as on the previous page, which I will bring back. It is also not equal to 0 or 9, and I'll explain that in a moment. Then x2 will not be equal to b sub 2, or 0 or 9. Similarly, x3 will not be equal to c sub 3, or 0 or 9. And we continue this until I get all the decimals out to infinity. Now, let me go ahead and tell you, first of all, why I am forbidding 0 or 9. We forbid, and I'm constructing this so I can make this any way I want, we forbid 0 and 9 so that, first of all, x will not turn out to be 0.000 out to infinity, which is 0. And 0 is not in the interval, that's one endpoint. Also, we don't want x to be equal to 0.999 out to infinity, which of course is equal to 1, and that's another endpoint. And x is not ambiguous in its representation. Ambiguous. Such as, like, for example, 0.4999 out to infinity is equal to 0.5. We don't want to have an ambiguity so that x in one form might not be there, but its other form might be there. We want to make sure that x is represented only one way. Now, why did I not make them equal to A1, B2, and C3? Well, look back here. Remember that these were the first three in my particular listing here. I'm saying that x1 is not equal to A1, x2 is not equal to B2, x3 is not equal to C3. So that's going to make x different from this one, and this one, because it differs in at least one decimal place. So let's see what sort of conclusion we can draw from that. Let me write down what I've got. But now, by the design or the construction, clearly we have that x is in the interval 0, 1. It's a decimal. And yet, x, which is point x1, x2, x3, etc., and I'll write this out this way, differs from the first one, point A1, A2, A3 out to infinity in the first decimal. So it differs right there, as I mentioned on the previous page. So it differs in the first decimal. It also differs from point B1, B2, B3 in the second decimal right here. So it's not equal to that one. It differs from, you see where this is going, C1, C2, C3 out to infinity. It differs in the third decimal. So it doesn't equal that one, so that they cannot be the same decimal. And this goes on forever. Well, that means that x is missed by the correspondence. Missed by the supposed, see, we now are suspicious of this, supposed matching. Okay, the supposed matching. Meaning, since the matching or that correspondence was arbitrary, it means that the claim that we had above is contradicted as we hoped. Well, if the claim is contradicted, what does that mean? Well, the claim was that there was a correspondence, therefore, thus, 0, 1, and hence all of R is a strictly larger set than n, the natural numbers. And that's the end of the proof. We have shown that the real numbers, in fact, an interval of the real numbers, is alone strictly larger in an infinite sense than the natural numbers. So that's rather surprising. And it shows us that there's more to infinity than perhaps you have realized in the past. So I hope you enjoyed that.